Let's take a look at this serial EEPROM from Microchip. I will review the features and chip pinout, the instruction set, the MyRio SPI interface VIs, and then setting up the read and write sequences. This is the serial EEPROM that's included in the NI MyRio Embedded Systems Kit. This is the Microchip 25 LC040A. This is a 4 kilobit SPI bus serial EEPROM. ROM stands for read-only memory, and that implies that it's non-volatile memory. Retains the data when the power is removed. P stands for programmable, and EE stands for electrically erasable. Let's review the important features for this device. It provides 4 kilobits of storage, and these bits are arranged as 512 8-bit bytes. You can write individual bytes or multiple bytes, and when writing, you can write up to a 16-byte page size in a single write cycle. You can read as many bytes as you like, however. The address pointer auto-increments. The device has a self-timed erase write cycle of up to 5 milliseconds. It supports a write protect pin called WP, it's active low. It's rated for 1 million erase write cycles with data retention of more than 200 years. The supply voltage is 2.5 volts to 5.5 volts. Looking at the SPI bus, it supports a maximum clock frequency of 10 megahertz. In addition to the external write protect pin, there are 2 bits in the status register for doing a block write protect. You can either protect none of the array, all of the array, the upper half, or the upper quarter. There are numerous applications for EEPROMs, and I'll just mention a few. They are handy for any kind of embedded application where you need some sort of external non-volatile memory. They could serve as the key for a digital lock, especially because many smaller package styles besides the DIP pictured are available, so you could make a very small key that way. You could also use this device to store a sensor calibration table that's unique to the specific characteristics of that sensor. Let's review the pinout for the 8-pin DIP style package. This cutout orients the device, and the little circle indicates pin 1. We have the standard pin numbering scheme for DIP style packages. Pins 4 and 8 are the power and ground connections. Pin 1 is the chip select, and the little bar indicates that it's an active low signal. The write protect is on pin 3. An input called hold is on pin 7, and then the 3 remaining pins are associated with the SPI bus. This is the serial clock, the serial input to the memory device, and the serial output from the memory device. All right, let's take a look at the instruction set for the EEPROM. We have 6 instructions altogether. Begin with the main instructions for reading and writing data. These are 2-byte instructions. In the first byte, most of these bits define the instruction, and then you also need to insert the 8th bit of your address. The second byte would be the remaining 8 bits of the address. This is a 9-bit address, and it defines where you begin reading or writing. Here we have an important instruction called set the write enable latch, and this is a bit inside the status register. This one is only a single byte instruction. Here we have a pair of instructions associated with reading and writing the status register. Now the status register is laid out like this. The upper 4 bits are of no use and always read back as 0. The write enable latch is located right here in bit position number 1. That needs to be set in order to allow a write to the device. WIP stands for write cycle in progress, and that's a status indicator bit. The remaining 2 bits are the block write protect bits. These are read-write bits. The other 2 are read-only bits. Here's the table for the 2 block protect bits. You can protect some subrange of the memory array, or none of the array, or all of the array. These bits are non-volatile, just like the rest of the memory array. Now I'd like to show you the SPI-related VIs that are available on MyRIO. Begin with the Express VI. You can select the channel as either connector A or connector B. These are the MXP connectors. This is a reminder of the pins on that connector. You can use the write and read modes, but do not use the write-read mode. That's only for simultaneous read-write, which is not supported by this device. You have up to 4 megahertz available. We need 8 bits for the frame length, and you can go ahead and use the defaults for these advanced options. These are all correct for this particular EEPROM from Microchip. Looking at the low-level SPI VIs that are available, these are under the Advanced I/O subpalette of the MyRIO area. Again, we don't want to use the simultaneous write-read. Click the View Code button to find out how to use these low-level sub-VIs. Here we have Smart Open, which operates essentially just like Open. There's Configure. We see all of the options laid out there. And here we have Write, which is driven by a 16-bit unsigned integer array. You need to use the 16-bit data type even for 8-bit bus transactions. Looking at the read version, you see it's very similar in terms of configuration setup. Here you indicate the number of bytes that you would like to read, and that number is returned in the array output. Should also point out that the array length indicates the number of bytes that you intend to write. Now let's look at the sequence associated with reading data from the array. You begin by asserting the chip select. You can use the Digital Output Express VI or low-level VI to send that line low. You then issue a read instruction at the desired starting address. For example, supposing you're doing address hexadecimal 142. The first and second bytes would look like this. Now the most significant address bit is A8, and this must be inserted into the first byte. The second byte then is the remainder of your 9-bit address. Next, we read the desired number of bytes, the EEPROM address pointer auto increments, and then finally you deassert the chip select by sending it high. Writing data to the array is a little bit more involved. First of all, you need to ensure that the write protect pin is held high. First, begin by asserting the chip select as before, then issue the write enable instruction. This bit is unused in the instruction. I'll just take that as 0, and we have that hexadecimal 06. You then deassert the chip select for at least 50 nanoseconds, and this sets the write enable flag in the status register. Again, assert the chip select, and now issue the write instruction. For example, supposing we're trying to write at address hexadecimal 0ED. Again, you pick off the most significant bit for the address and insert that into the first byte. You can then send up to 16 bytes to write. You then deassert the chip select and then wait for 5 milliseconds for the self-timed erase write cycle to complete. Reading and writing the status register byte follows the exact same sequence as what I outlined previously, except you'd use the read status register and write status register instructions. Now, reading out all 512 data bytes from the EEPROM is easy. You just start at address 0 and read out 512 elements. Writing to the entire array, that takes a little bit more work. The array is 512 bytes altogether, and then within that 512 bytes, running from address 0 to 511, every 16 address locations is called a page. This is page 0, 16 bytes, page 1, page 2, and so on. And I've outlined the page boundaries here. Now, a single write operation must be within a single page. The address pointer will wrap around when you attempt to write more bytes beyond the page boundary. For example, supposing you started writing at this address right here in the middle of page 3. You're good up until the end of the page, but after that, the internal address pointer immediately wraps around back to the beginning of that page and continues writing. Now this will overwrite any previous bytes that you might have issued in the instruction. Therefore, you will need to issue the complete write sequence, that is, dropping chip select low, issuing the write enable instruction, toggling the chip select, writing the data, raising chip select, waiting 5 milliseconds. You need to do that complete write sequence for every page that you write. Note that the write enable latch automatically clears after a successful write sequence. That's why you have to initial the write enable instruction for each page. Finally, let's look at the hold pin. This is an active low pin. You can assert or drop low when the serial clock is low to suspend serial communications already in progress. That's useful to service a high priority task without restarting the SPI bus transaction. All of the SPI related signals go to high Z so that other devices may use these lines. You need to deassert the hold when the serial clock is low to resume the transaction. And finally, observe that the chip select must remain inserted the entire time that the hold signal was low.